Good morning, everybody. Mr. Bourne here. I'm going to talk to you this morning about nuclear fusion, which is a very interesting and exciting topic in physics. So we have nuclear explosions, we have supernova explosions, we have stars, and we have nuclear fusion reactors. So exciting stuff. Let's move on. So at the heart of nuclear fusion, we have nuclei joining together. Okay, so different, the opposite of nuclear fission, which is the splitting of large nuclei like uranium. Fusion involves joining things together, fusing them together. So what goes on inside most fusion reactions? We have two isotopes of hydrogen called deuterium and tritium. We simply refer to these as D and T. Now these are both types of hydrogen, though you won't see their names in the periodic table. They are isotopes of hydrogen. They are hydrogen though because they only have one proton. There it is, there's proton there, and there's the proton there. The other two things, the blue things, are neutrons. So this is two types of hydrogen. They join together, so they must approach each other at very, very high speed, which is very high temperature. If it's hot enough, they will stick together and they produce a bigger atom or a bigger nucleus called helium. And also a neutron is released as well. But importantly for us, vast amounts of energy are released in this type of fusion reaction. And we can use that energy for destructive or for constructive purposes. Let's move on. So first, let's look at destructive uses of nuclear fusion. So nuclear weapons, the most deadly form of weapon ever devised by the human race, are nuclear fusion bombs. Now, in the Second World War, the Americans developed nuclear weapons and they dropped them on Nagasaki in Japan, killing 100,000 people. So destroying a city with one bomb. Nobody had ever seen anything like that before. It was called Fat Man. There it is. Look, there's Fat Man down there. It was dropped from a plane. And the destructive power of this bomb is equivalent to 15,000 tons of dynamite. So absolutely huge. The UK government is thinking whether we should invest money in the next generation of Trident missiles. Each of those has a destructive power equivalent to 100,000 tons of dynamite. So incredibly destructive. The Russians have the most powerful nuclear bomb. It's called the SS-19. I believe it's an intercontinental ballistic missile. It has a destructive power equivalent to 5,000 tons, 5 megatons of dynamite. Sorry, not 5,000, 5 million tons of dynamite. So one of those would destroy a big city like London. It would just flatten it completely and kill millions of people. So these are awesomely destructive bits of technology. Huge amounts of energy locked up inside something which isn't very big. But we can use fusion for very constructive purposes. So this is a photograph of the inside of the Joint European Torus, which is based in Oxford or just outside Oxford. It has a donut shape, so hydrogen can whiz around inside this. It's a donut shape of a room. It has very powerful magnetic fields to keep the hydrogen inside it. It gets very hot in there, millions of degrees, so hot that the hydrogen nuclei will slam into each other with enough speed to actually fuse. Remember, they have to overcome the repulsion of the two positive protons. So it takes enormous temperature, millions of degrees, to do that. The next generation of fusion plants, the next one will be built in France. It's going to be called ITER. You can watch this video if you like, if you'd like to find out more about that. It hopefully will be, we don't have to put more energy in than we get out. That was the problem with this one. We actually put more energy into it to make it work than we got out. So that's not viable, but we've learned huge amounts from this, and we're now building this next generation ITER, and hopefully this will produce more energy than we have to put in. So exciting project down there in France. The core of our sun produces energy through the process of nuclear fusion, so life on Earth depends upon fusion. So deep inside the sun is the core. In here we've got fusion reactions taking place. Hydrogen fuses with hydrogen to make helium. Huge amounts of energy are released. You can imagine that the sun is many, many millions of times bigger than a nuclear weapon. So that gives you some idea of the amount of energy coming off the sun. Absolutely staggering. All of that energy comes out as light and heat. Okay, so even though the Earth is millions of miles away, we still feel the heat and we see the light of the sun very, very brightly. So the sun is powered, all stars are powered by nuclear fusion. So how are stars formed? Well, it all starts with a gas and dust cloud. Hydrogen gas floating in space, vast clouds of it. Eventually gravity is going to start pulling it all together. Remember that anything with mass will attract to itself and to other particles. So it takes a long time this, but eventually all of those gas particles, they start to be attracted to each other, they accelerate towards each other. It takes a long time, and they eventually the cloud gets smaller and smaller and smaller, gets hotter and hotter and hotter, and eventually in the center we get some nuclear fusion as those hydrogens are now traveling fast enough to slam into each other to start fusing. It's called a protostar, which literally means young sun. Okay, let's move on. So how are stars formed? I'm going to quickly go through these. You can play back and look at them again if you like. So gravity causes particles in the dust cloud in space to attract each other. The dust cloud gets smaller, hotter, and start to spin faster. Heat is produced by the conversion of gravitational energy to kinetic energy. Eventually the cloud is so hot that nuclear fusion can start. Heat and light energy are produced and a protostar is born. So after the protostar, the stars enter the main part of their life, which is called the main sequence. There we go, look, main sequence. And a star will stay like this in a very stable place for many billions of years, which is good news for life on Earth. So let's go through the text at the bottom here, just to point out very quickly that there are two forces acting on the sun at this stage of its life. There is the inward pull of gravity, call that G, but there is also the outward pressure caused by all of the nuclear fusion. We call that radiation pressure. It's an outward force, and these two forces are balanced. Okay, so I'm going to go through the text underneath if you just follow it with me. Once a star starts shining, it enters its main sequence. The sun is a main sequence star and has been like this for billions of years. The pressure of the continued fusion reactions tries to push the star outwards. Gravitational attraction causes the star to contract inwards. These two forces are balanced, so the shape of the star does not change for billions of years. Let's move on to the next one. So, stars, depending on how big they are, go through life in two different ways. Our star, the sun, is a small star, and it will follow this route down the left here. Okay? Massive stars, on the other hand, I can think of a couple of famous examples, Betelgeuse and Aldebaran. They will go down the right-hand side path down here. Okay, so let's start with a small star like the sun. It starts off as a nebula, which is a cloud of gas and dust. It contracts, gets hotter, fusion starts and produces a young star called a protostar. The sun will then go into its main sequence of steady hydrogen fusion. Hydrogen fuses to become helium, and it's got a yellow color. Yellow because even though it's hot, it's cooler. It's maybe several million degrees, which is very hot, but it's cooler than some stars. And it's a bit like a Bunsen burner. Bunsen burner has two flames: a yellow flame, which is hot, but it's not so hot, and then the blue flame, which is very, very hot indeed. So our star is a yellow main sequence. It then, once it runs out of hydrogen, the star swells up to become a red giant. It will swell up. Mercury and Venus will be swallowed up, and it will reach as far as the Earth. And at that point, life on Earth will be destroyed. But that's not for another 2 billion years, so we've got plenty of time to find another planet to live on. After that, once it runs out of all of its fuel, it stops fusing altogether. It then collapses down. It shrinks down to a white dwarf, which is still quite hot, but then even that cools down. It goes red, and then eventually even black once it runs out of any energy whatsoever. So at that point, the star dies. Now, massive stars, maybe several million times bigger than our Sun, they too start off as a nebula, a dust cloud, a gas cloud of hydrogen. That gas and dust contracts and starts to fuse into a protostar, but of course much bigger. It then becomes a main sequence star of steady hydrogen fusion, but it's blue, much hotter. And because it's hotter, it's using up the hydrogen much more quickly. It doesn't last as long as our Sun. It will use up its fuel in maybe a few 100 million years, not billions. It then becomes a red supergiant. The whole star swells out. It becomes absolutely enormous. And that, you can imagine, is not going to just fizzle out gently. It's going to go with a bang. And the red supergiant, indeed, once it runs out of fuel, it collapses and it becomes a gigantic explosion called a supernova. Supernova is the star explodes outwards and it outshines the rest of the galaxy for about 3 days, producing enormous amounts of light and heat. An absolute spectacle if we could see it. And what's left after the explosion? Well, two possibilities. We think there might be something called a neutron star, which is a very, very dense object in the center where all the atoms are packed together. Well, it's just solid neutrons all the way through. Very, very dense. Alternatively, we think there might be a black hole, which is so intense, so dense that not even the gravity becomes so strong that not even light can escape. So let's have a look at these descriptions of a supernovae. So only a massive star, our Sun, will not become a supernovae, but a large star like Betelgeuse will. The star will eventually die when the nuclear fuel, the hydrogen, runs out. These stars can keep fusing until they reach iron, atomic number 56. After that, no more fusion can take place. The star at that point collapses under its own weight. As it collapses, it sends a huge shock wave out through the star, which blasts the star apart in a spectacular explosion called a supernovae. And there is a picture of one there. And we do see these things, not in our own galaxy, but they do happen in other galaxies, and astronomers can use these to measure the size of the universe. And elements above iron are produced in this colossal explosion. So let's move on to black hole. Now, a black hole is the remnants, we think, of a supernova. What's left has become so dense, it's become infinitely dense. Professor Stephen Hawking, this has really been his area of research, and he's become famous for his theoretical predictions of what might happen to a black hole. But it's so intense, gravity is so strong, not even light can escape. Hence the name black hole. Black holes feed on any matter that falls into them, and they grow in size. If you were unlucky enough to fall into a black hole, so there's a body there, look, falling in to a black hole, you would be spaghettified, which means stretched out into long, thin object, because the gravity on your toes would be millions of times bigger than the gravity in your head. You'd be sucked in and spaghettified, and we don't know what happens if you fall into a black hole. So the subject of science fiction novels. They grow in size as they feed on matter falling in. We think there is a black hole at the heart of the Milky Way, but we don't know for sure. It's an area of research. Let's move on. So here is the life cycle of a small star. Nebula, protostar, yellow dwarf, red giant, white dwarf, red dwarf, black dwarf. I'll quickly go through those descriptions. Look, you can stop the video, replay it. You can read those. You need to know each of those stages. You also need to know what happens to a large star. So again, you'll notice that there are different stages here. It's a blue main sequence, it's a supergiant, it's a supernova, a neutron star, and finally a black hole. Here are the stages, so you can read those, and you need to try and learn those as well. So thank you for listening to this interesting topic of fusion. Please look at its learning. There are some questions on past papers there to download. I want you to have a go at those and bring them in, please, to school where your teachers will check those. So thank you, and good luck with your revision.